Assalamualaikum and hi everyone, this is Dr. Shazira, and in this video we are going to be talking about Newton-Raphson method. Okay, so I'm going to show you the basic or the concept of Newton-Raphson method. Consider this diagram where you have a function fx, okay, denoted by the curve in blue color. Okay, and we can see that the intersection point between the curve and the x-axis, okay, denote the root, okay, of the function fx. Okay, so it means that this node here is actually your actual root that you wish to get. Okay, so let's assume this is your x star here to be your actual roots. Okay, but in the Newton-Raphson method, okay, so the first time we should have somehow our initial point to be started with. Okay, so assume that value to be x naught. Okay, so basically we can choose any value to be starting with. Okay, so I'm going to assume we have somewhere here is our x naught. Okay, that is our x naught, and our intention, okay, is to get the roots of fx. Okay, so we are hoping to go to the left until we reach x star. Okay, so now correspond to the x naught. Okay, so we know that, okay, correspond to this x naught, so we know somewhere at the top here, okay, at this point, somehow we know that at that location it is x naught, fx naught. Okay, because when x is x naught, so somewhere here, okay, the value is of course fx naught. Okay, okay. So now what do we do next? Somehow we know that the length, okay, between these green dot here, okay, down here to the x-axis, okay, the length is basically fx naught, okay, because we know somewhere here is fx naught and somewhere here is the origin 0, so the length here is somehow fx naught. Okay, and then, okay, so at this point here, okay, so if we take the slope, okay, at that point, I'm going to write the slope. Okay, so the slope, okay, the slope at this point here, okay, at this point here is equal to the, okay, the derivative of the function fx, okay, evaluated at x naught. So it means we have f prime x naught. Okay, I'm going to repeat. Okay, the slope at this point is actually equal to the, finding the derivative of a function fx, okay, at the point x naught. Okay, so the slope is basically f prime x naught, and we know that the derivative f prime is actually, okay, in a layman terms, we know that this is rise over run. Okay, rise over run. What is rise? What is run? Okay, so rise is actually the changes, okay, in terms of y here, okay, and the run is again the changes in terms of x. Okay, so now if we take the tangent line, okay, at this point here, if we take the tangent line, if we draw a tangent line, okay, we have, more or less something like that. Okay, mind you, my bad sketching. Okay, so now, okay, consider that tangent line. So this value somewhere here is now x1, okay, because initially we start with the x naught. Okay, so the next value of x that we have, we consider as x1. Okay, the distance that you can see here, this is the run. Okay, so the run is equal to the x naught minus x1. Okay, because obviously x naught is, being more to the right, okay, compared to the x1. So of course the value of x naught should be higher, okay, compared to the x1. Okay, so the length here is basically x naught minus x1. Okay, so this is equal to the fx naught. Okay, the rise if fx naught over x naught minus x1. Okay, so now what do we do next? Okay, so if we take out this guy here, so now we have fx naught over x naught minus x1. Okay, so x1 here, for the first time, it is the approximation to our root that we wish to get. Okay, so x1 here is the only term that you don't know yet. Okay, in this expression, x naught is known, of course. Okay, that is your starting value. The function itself, okay, the f should be known. Okay, so that of course you can get the fx naught as well. Since you know the x naught, so of course you can get the fx naught. Same thing to the f prime. So this is known. This is also known. X naught is also known. Okay, so what we wish to get is x1. So if we rearrange the expression, so easily we can get, okay, x1 equals x naught minus fx naught over f prime x naught. That is the first time, the first iteration. Okay, so you can get that. But based on this diagram here, x naught is still not, okay, the root that we wish to get. But somehow, okay, we can see that if we have another triangle here, so it means if we sketch that, okay, we take the point here and draw another tangent line at this point, so we have something like that. Oops. Okay, it should be a straight line anyway. Okay, so now this value here is now to be your x2. Okay, so you see, you are getting closer to the actual roots that you want to get. Okay, so if we, using the same explanation as before, so it means if we take out that small triangle where this is x1 and that is x2, and the length here somehow is fx1, because at this point, okay, the reading is x1 fx1. So the length, okay, the rise is fx1. Okay, so the formula, okay, for the x2 then will be x1 minus fx1 over f prime x1. Okay, so now you can see the pattern. So this is at the first iteration and this is at the second iteration. So maybe you need one more, okay, to get your root here. So we have another triangle. So now you see you are we can see at the point, okay, on the point of the root itself. Okay, so based on the pattern, so it means that if we want to write x3, then it's going to be x2 minus f x2 over f prime x2 somehow. Okay, so based on the pattern, we can write therefore xi plus 1 equals to the xi minus f xi over f prime xi. So this is what you have, okay, in the algorithm of Newton-Raphson, or this is basically Newton-Raphson formula. Okay, so you can see the formula is actually just comes from the knowledge of the calculus, where you use the tangent line, get the concept of slope, okay, and you can see, we can come out the Newton-Raphson formula. Okay, as compared to the bisection method. Okay, so if we are talking about the bisection method, so in the bisection method, so you start somewhere here. This is your A, and now this guy at the X naught here will be your B. Okay, in the bisection method. So in the bisection method, so at the first iteration, you are going to get your C, right? Okay, so you are going to divide A and B into, two smaller intervals. So maybe the first time, this is your C somehow. Okay, so you can see the what a Newton-Raphson can do. Okay, so at the first time, at the first iteration, you see by having this tangent line, you can see you have x1 to be your first approximation, which is, we can say it is closer to the roots compared to the C that we have here. Okay, so in general, the Newton-Raphson working or the convergence is faster compared to the bisection method. Okay, so that's the explanation, or how we come out the formula for the Newton-Raphson method. Okay, so that's all. Bye bye and thank you.